Everybody content? Well, thank you very much, Joe. I appreciate your presentation.
You're welcome.
Without further ado, let's get on to Bill. Introduce yourself, Bill, and the floor is yours.
Well, is that for me? This is Bill.
Oh, crap. I'm sorry. I meant to mute another guy, and then Bill's name jumped on top of it. Sorry, Bill.
Okay, ready for me?
Yes, it's yours.
Good. The good news, the world's been waiting for. The tech got my fiber optic hooked up, but my other computer is might log on. Anyway, we will go into business here. All right, elevator logic.
Progress.
The on the 4th 2020 Facebook page, a fellow 2 months ago proposed simulating logic, still simulating elevator with Ford, and so I rose to the challenge. A couple of people have done it so far. They'll do it again, I guess, in 2 weeks. Let's see if I can clear up the screen. There we go. All right, so my version of elevator logic. The goal on this is to simulate an elevator, single elevator that you'd have in a building. So it could, in this case, I'm doing a visual model. And how else would you want to do an elevator except to look at it? I did a 6-point problem statement. First, my building has 10 floors, and they're labeled ground floor 2 through 10. I know in Europe, floors often go ground floor and then 1 through 9. And in China, there's no 4th floor because 4 is the symbol for death. So anyway, the next step is the elevator has capacity for 5 passengers. This proved later to be and this is a very key element, very, very key. Looking to simulate a real elevator, most of the traffic is from the ground floor to upper floor or upper floor to ground floor. So, sure, from the ground floor, 35% is ground floor up, 35% is higher floors to ground floor, and then 70% is floor to floor. So on our model, you'll see a lot of G's popping up. The logic gets a little complicated because we only want the passengers when going up, and we skip floors when the elevator is full. So there are a number of subtle contingencies. And then in this demonstration, we make a little delay so you can see what's going on. The passenger action time is 1 second. Travel time between floors is 1 second. So this is the picture of what the building looked like. This is for early testing. You can see on the left are the floor numbers, G through 10. The dots represent passengers who are waiting. So every time a passenger call goes in on their floor, their destination number appears. On the right-hand side are the elevator doors, and you see they're all closed at the higher levels. At the ground floor, the doors are open. The 5 dots say there were no passengers waiting. Here's the actual live demonstration. We'll see this now, and we'll see it at the end. I do this demonstration now so you get a feeling for what the components are like. You can see the elevator on the right displays its contents. Right now it's moving down. I'll give a little dialogue on this, and then we'll go to the actual use. So on the ground floor, we have 5 ground floor passengers exiting. So every time a passenger exits, we add 1 more call. So there will be exactly 10 calls open at all times. Now we load floor 3 from the ground floor. We go up to floor 3, and the 3 will disappear. We add the 4 because there's a call to the 4th floor. We go to the 4th floor. We drop that 4 passenger, and there is no more calls down. So we go all the way up to the top, clear up to the 9th floor, and we pick up 2 passengers, a ground floor call and a 6th floor call. Now we go down to the 7th floor and we pick up 1 more passenger. We go to the 6th floor and we drop off the 6th floor. And of course, we'll be adding another passenger, another call along the way. We pick up the 2nd floor passenger. Now the elevator is full, so we skip all further calls until the ground floor. Nope, we drop the passenger 2, we pick up 1. Now on the ground floor, we'll drop all 6 ground floor passengers, all 5 ground floor passengers, and we'll pick up the 2nd floor passenger and we'll head up again. All right, you get a general feeling for the operation. So here's the driving program. As you can believe, we start out with a begin forever. There's a pause inserted, and if I hit any key during the pause, the program will end. So this is the logic, and it's very clearly expressed. We start out with the elevator at the ground floor, and it's going to move upward. So we want to find the lowest floor where there is some sort of action. Either the elevator wants to go there or there's a passenger waiting. So we find that lowest action floor. Then we determine what service is needed, what floor it is. And now on the while portion, we go to the floor. So while there is service needed, we go to the floor. Of course, we process exits first because the passengers want to get out. Then we load in the up calls, and then we repeat. So this will repeat floor by floor by floor until we run out of service needed. By the time we're out of service needed, we're on the upper floors. The elevator will now reverse, and now it's high floor, and it's trying to find the highest action. So imagine it's on the 10th floor, and the highest action is 7. It will go down to the 7th floor and begin operation. But the same logic. We look for a down service needed. We go to the floor. We process the exits. We load the down calls, and we repeat. So this will stop at each floor, down, 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 until we get down to the bottom. And then we are out of high actions. So we move to the again and start over. This is a quick look at some of the code. For readability, I have replaced some of the code with what it actually does. So this lowest action floor, the logic says over all of mark the floor and leave, exit at floor I, and so mark and leave and loop. Same way with high action floor. The purpose of this action floor is to develop the parameter for the while. And so when I say mark and leave, that means initiate action for the while portion. Here's how we exit the actual code. F slots is 0, sets up a do loop. F slots is 5 because there are 5 elevator slots, and then the all determines if the elevator is vacant, and it assigns the call. Elevator motion to go floor to floor, that's a 2-floor command. So in this case, we give the floor to and the floor from, and then we skip if the 2 are equal because there's no motion if the elevator wants to go to the same floor. Otherwise, it'll move to a high, with a true value, it'll move to a higher floor, else move to a lower floor. In this case, now we are, this is see the caret, left bracket, right bracket, caret, that shows the elevator in motion. So as we're moving to a higher floor, we show the elevator in motion. Then the do loop says we close the doors, we do a pause, we move to the next floor, and we show in process. So this is a chunk, floor by floor. Close the door, move to the next floor, close the door, move to the next floor. At the very end, then we show the elevator with contents. This is our logic for the 70% ground floor calls. In this case, we are picking a random number 1 through 9. So we use the built-in Win32 4th random number generator. it would normally generate a number between 0 and 9, 0 and 8. In this case, I generate 0 through 8, and then I add a 1 offset. So now I get 1 through 9. So that generated a single random floor. Now I need a pair of floors from and to. So in this case, I do the get a floor number twice. And if they're equal, I repeat and do it again. So this will get 2 floor numbers until they are different. And this creates a trip. We won't go into the logic, but the 100 random proportion, that forces the calls to be non-ground floor. The non-ground floor calls 30% of the time, and the remainder then forces them to be 70% involving the G floor. Visual components with 4 pretty nice to print closed doors. I have a word that is right bracket because it's printing the doors as it's on the center. So that is an elevator greater than XY. This is a similar approach when the elevator is moving. It does the very same positioning, and it shows the elevator with the little brackets on each side, or the little greater than less on each side, which shows it's in motion. And then finally, this is the dot elevator, which actually shows the elevator in use. It prints a left bracket. We go into the number of slots. We find the contents of them. We print the symbol. And the symbols can be a dot, or they can be a G, or they can be 2 through 9, or 2 through 10. Again, the dot symbol is either put a dot for no content, or it'll put a G if it's ground floor or 0, and then the balance shows 2 through 10. Okay, this is writing the elevator. This shows the building. This was early development work. So basically, the elevator draws the elevator on the ground floor and on the floor, hull floor. Dot building shows all the floor levels, and it shows the elevator at the ground floor. So this is one of the very first items that I wrote just to get the building to display. We'll go back and show our operation again. By now, you're quite familiar with what's going on. Moving down. And you can appreciate the logic that's going on, where the elevator will be full, being elevator is full. Now we skip 3 people on floor 2 because the elevator is full. Now we drop all the ground floor people. We reverse and go up. Now I found that having a dynamic 10 passengers all involved and an elevator capacity of 5, we do a fair amount of skipping where the elevator is full. And so I think one occasion, a passenger on the 2nd floor got flipped twice, skipped twice, because the elevator came down full past floor 2. So this is a very frustrating case for a patron because they can literally see the elevator light on the wall showing that their floor has been skipped twice. A study like this could be used dynamically to figure out capacity handling on an elevator. And of course, we know there are more elevators. The stack is normally 3. I'm not sure why it's 3, but the most common stack in the buildings are 3 elevators. So when one elevator reaches capacity, then they can position the second elevator to fill in, and then the logic gets really complicated. So we will skip over the demonstration. One last floor on here. We're going up to floor 2. We're going to drop a couple. We'll skip floor 4 because the 3 is a down call. There. Now we go up to 5, and we drop 1 passenger. We go up to 6, we drop a passenger. 7, we drop a passenger. Skip 8, 9, drop a passenger. We're going to come down again now, and we got called to the ground floor. We'll go all the way down the floor, pick up 2 passengers, and so on. This is a cute little demo. Occasionally, I've just let it run in a window up at the side of my computer. It's not doing other work. It's just fun to watch the elevator work. Of course, the numbers are all random, so we every time the movie. So of course, whatever this movie shows is always the same. But every time you start this program, you will see a different set of elevator patterns. So summarize. We started out with a 6-step problem statement, which made it a very direct implementation. I basically just started implementing each thing as I came to it. The simple things at the beginning, like showing the elevator and making the elevator move, and then the more complicated steps after that. This was a significant effort. For the last 2 weeks, I spent at least 12 hours on this. It was kind of fascinating. I did a little fill-ins and gaps. I worked on it a couple hours and go. And I ended up rewriting it. A chunk of it was learning how to program the scrolling on the screen. Notice the elevator is always in a fixed position, even though that screen will normally scroll. So it was print something on the building and then restore the cursor back where it was. So that was a learning little trick I had. As I mentioned before, the 10 active passengers tends to overwhelm the 5-passenger elevator. My code is written so that the number of floors in the elevator capacity is parameterized. So I should be able to recompile that program with an elevator capacity, say, of 8, and then I suspect we would have no contention for elevator space. As I said, I rewrote the program roughly 3 times to kind of back up, and when I learned from the later stages, I'd clean up the early stages. The first pass was to simulate the building in the elevator. The second pass was to get the elevator motion and floor actions up and down, finding floors that needed activity and support. And then I found out we weren't passing, we weren't skipping people right. So finally, the third pass was to control the pickups on the way up and similarly on the way down to simulate real life. That concludes my formal remarks. And so I will yield the floor back to Kevin.
Okay, are there any questions, comments, slanders, libels?
A lot of comment from me. Bill, that's a really excellent program you have there, especially adding, maximum capacity. One of the things, like I said, one of the things I wanted to do was marry a preemptive real-time operating system of Forth, which would really make that code simple to write. So you could prioritize things, because really what you want to do is make this code event-driven, which means the events are when a person on a particular floor pushes a button to another floor. That would be an event. You want to make sure that the system gets that event and use it up. And also you could add things like, if there's a fire in the building, usually what happens is all the elevators go to the ground floor. Let's say you're in a medical building. Well, you want to make sure, because some of these people won't be able to go downstairs, say they're in a wheelchair. Well, you want to be able to get them in the elevator and be able to go down. Okay, so you might have to work things out. I mean, the fire department would have to work things out and how that's done, based on their requirements. But I really like this algorithm that you come up with. It's really nice. Now, in real world, my mouth is not working. You may want to have a load sensor in the elevator so that you don't go over maximum weight. Okay. And I think that would be a nice thing, a nice addition. And Well, that's all my comments are, because I'm running out of energy. Yeah, I'll tell you, I'm dying right now.
I think that the thing that I don't see in real elevators is where it fills up and it's full, but it still stops at intermediary floors and nobody can get on. I guess that would be implemented with the weight sensor, but all elevators have a weight sensor and they complain if they're overloaded.
Oh, okay,
Well, my example does have a weight sensor. The weight sensor is basically 5 people. So
right, yeah, you count 1, 2, 3, 4, 5. Oh,
the elevator capacity is 5 people, and that's based on, you know, the elbow room or the average weight. So this elevator is smart enough to skip floors when nobody can get on. The Fourth 2020 Facebook group approached it slightly differently. The problem statement was a little bit different, and there they are doing more of a human interface modeling. So they have up buttons and down buttons, and you click on the screen to signify up and down calls. Their logic is nowhere near as thorough as mine is, though, I'd say. Also, Peter Forth, the leader of the group, actually went out and made a physical model of this. He took a vertical rack, put a servo motor at the top, took a cardboard box on a fishing line, and now he has that box moving up and down in the rack to different floors. So he has simulated the actual elevator moving up and down and doing it on an ESP32 chip. So there is, you know, I'm emphasizing logic and he's emphasizing real time. Any other questions?
I noticed when you sent your email that there was no rule 6. You went right from 5 to 7. Is that an homage to the University of Wallabaloo Logic and Philosophy Department? All right.
Not a question for me.
Yes, Bill.
What was it again? I didn't get it.
It was just my feeble attempt to be amusing. There's no rule 6 in your challenge. You go right from 70% of all elevator activity is to or from the ground floor. It's rule 5. And then rule 7, only stop at floors with down passengers calls when going down, and conversely, skip up calls when traveling down. So what was rule 6?
there is no rule 6.
My numbering may have faded away. Let me go back and look at my own stuff.
Okay, so there are only 6 rules, and there's no rule 7. But yeah, Monty Python years and years ago did a skit where these guys were listing rules, and they said, rule 6, there's no rule 6.
There is 6 rules. Travel, the 6th rule of travel time between floors is 1 second.
Okay.
Anyway, okay, back to work.
All right. So in the Bay Area, as in many other places, there was a long tradition of hams meeting to have swap meets. And it evolved into, at least in the Bay Area, an electronics, more general electronics flea market. There was a time when there were a lot of computers of the PC and mini computer variety. That's kind of tapered off. But a fine tradition, and one that has been revived this month. And it Dave will hopefully show some